Space is an incredibly unforgiving place. For the unbelievably complex machines we send up there, there's really no roadside assistance. So when something goes wrong with an asset that's worth hundreds of millions of dollars, how do you even begin to find the problem? Well, today we're diving into a really fascinating piece of research that proposes a smarter, much faster way to play detective on a satellite.
This really is the heart of the challenge, isn't it? You can't just send a mechanic up there. You can't just reboot it and cross your fingers. For a mission to survive, that satellite has to be smart enough to diagnose itself, pinpointing exactly what's wrong from millions of miles away. It's truly one of the biggest hurdles in keeping our critical space infrastructure alive and kicking.
So, to really understand the problem, we first need to meet the unsung heroes of satellite stability. Think about it. For a satellite to do its job, whether that's taking Hubble-like pictures of deep space or beaming down your GPS signal, it has to be pointing in precisely the right direction. And maintaining that perfect aim is a constant, incredibly precise balancing act. The key players in this balancing act are these remarkable devices, control moment gyros, or CMGs. Now, I know the definition here sounds a bit dense, but the concept is surprisingly elegant. You know how a cat always lands on its feet? It twists its body and its tail in midair to reorient itself. A CMG does pretty much the same thing for a satellite. But instead of a tail, it uses a super fast spinning flywheel to generate these powerful gyroscopic forces that can turn a multi-ton spacecraft with just astonishing precision. And get this, a satellite doesn't just use one of these. It uses a whole team of them, usually 4, all arranged in a pyramid shape. By working together, this little cluster of gyros can tilt and turn the satellite along any axis it needs to. It is a delicate, continuous dance of physics that keeps our eyes in the sky pointed exactly where they need to be. But what happens when one of the dancers in this orbital ballet starts to falter? These CMGs are mechanical devices, and they can fail. When the satellite starts to drift off course, Mission Control has this massive diagnostic puzzle on its hands. Which of the 4 CMGs is acting up, and how badly is it broken? Answering that question, and answering it quickly, can be the difference between saving a mission and losing it completely. And, well, the old ways of finding that faulty part weren't so great. Methods like neural networks needed tons of training data, they were slow, and honestly, they often couldn't pinpoint the actual problem. They might tell you, hey, there's a problem with the gyro system, but they couldn't tell you if it was, say, gyro number 2 that had lost 30% of its effectiveness. What engineers really needed was an ideal solution, something fast, precise, and smart enough to just work on its own. And that brings us to the really clever solution proposed in this research. It's called a hierarchical approach, which is basically a fancy way of saying it's a 2-step process. Think of it less like a single overworked detective and more like a super efficient 2-person investigation team. So here's how that team works. Step 1 is the sentry. Its only job is to watch the satellite's performance 24/7. It's not looking for anything specific, just for anything that seems, off. If it spots a deviation, it raises an alarm, and only then does it call in step 2, the investigator. This is the specialist. It activates using more computational power to dig deep and figure out exactly which CMG is failing and by how much. This 2-level system is just incredibly efficient. Okay, but what makes the investigator part of this duo so special is its breakthrough technique. See, it doesn't waste time checking every single possibility under the sun. It uses a much, much smarter search method to find the culprit. Let's just compare the approaches. The old method, a brute force algorithm, would test dozens of different potential fault values for every single parameter. It's like trying every key on a massive keychain. But the new method, called GAY-FKF, is far more elegant. Instead of checking 100 different values for, say, a gyro's efficiency, it asks a simple binary question. Has this gyro's efficiency changed from its baseline? Yes or no? It's just a much more focused way to search. The sheer scale of this improvement is what's really striking. The paper gives this great example with 2 fault parameters. The old brute force method would have to run 100 different simulations to find the answer. The new smart search method, it gets the answer by checking just 4 possibilities. That is a massive leap in efficiency, and it makes the whole diagnostic process dramatically faster. An elegant idea is great, but the real question is, does it actually work? Well, to find out, the researchers ran extensive Monte Carlo simulations, which is basically a way of saying they ran thousands of computer-generated tests that throw all kinds of random faults at a virtual satellite just to see how well their new detective could perform under pressure. And the results are, well, crystal clear.
The new method, GAUKF, correctly isolates the faulty component with an impressive 93% accuracy. That's a significant improvement over the older standard method, and it completely leaves the brute force approach at only 75% in the dust. So it's not just a more efficient search, it's a more reliable one too. So what's the trade-off? What does this higher accuracy cost in terms of time? Almost nothing. Compared to the standard UKF method, the new GAUKF approach gives you an 8.2% boost in accuracy for a tiny cost, just over half a second more in processing time. In the world of engineering, that is a fantastic deal. All right, so let's zoom out. A few percentage points of accuracy, a few seconds of calculation time. Why does this technical detail matter so much in the grand scheme of space exploration? This quote from the paper just says it all perfectly. The goal isn't just to know that something broke. The goal is to get such a detailed diagnosis, knowing which component and how much it has degraded, that the satellite can actually do something about it. It can reconfigure its own control logic to work around the damaged part, essentially adapting to the fault in real time. And this ability to adapt has huge implications. It means longer mission lifetimes and more reliable satellites. It means a more robust space infrastructure that can, in a way, heal itself. And ultimately, for missions where everything is on the line, a smart system like this could be the difference between a catastrophic failure and a mission that successfully keeps on going, even with a hardware problem. And that leaves us with a final thought. This elegant two-step diagnostic system is just such a powerful idea. So where else could we use a detective like this? Think about critical power grids, deep-sea exploration robots, or even autonomous cars. Any complex system where a hands-on repair is difficult, dangerous, or just plain impossible. The solutions we design for the harshness of space often find their most profound impact right back here on Earth.